Welcome everyone to this last lecture of today. It's quite late here in Paris. It's 9 p.m., but I don't know what time it is for you. It's not that late for Emily, who's in the United States. So I'm very happy to introduce Emily Barnard from DePaul University. Emily does algebra and combinatorics. Actually, our fields of research are close enough that we sometimes meet in conferences. So it's a pleasure for me to introduce her. Emily, the floor is yours.
Thank you so much. And thank you for being here, especially if you're up late and it's 9 p.m. and you want to relax. And I hope this is a fun talk for you. I had said to people who are joining that it's going to be a little bit interactive. So if you want to I'm hoping that we all get to have a little back and forth on Zoom here. So thanks for making the trek over, and yeah, let's go ahead and get started. Also, just since it's interactive, I hope you feel free to interrupt me with questions, either in the chat or you can raise your hand. All things are welcome. Okay, so hello, I'm Emily Barnard, and I'm going to tell you about my research. Okay, a little bit about me and kind of about what this talk is about. So I'm a mathematician. I am based in Chicago, Illinois at DePaul University, which is a fairly large university in the US. My job has two parts. I do research, and sort of the point of the talk is to show you what it's been like for me to learn to do research and what that can look like. And then the other part of my talk is interacting with students and teaching. I didn't know that I wanted to be a mathematician. I think even as a young person, didn't always really like math. It was a little later that I realized how much I liked it. And then even then, I didn't really know anybody. I didn't grow up knowing anybody who was a mathematician. I didn't know what this looked like. I didn't really know what it meant to do research. Maybe I had an idea of what teaching was because I had been a student, but it was all kind of new and I was learning it on the fly. Maybe this is a little bit like where you are right now too. You kind of like math. Maybe you know some people who do math, or maybe you're just kind of learning as you go, like, what does this even look like? So a little bit about this talk. The talk is going to start out with some math stuff, like things that I really liked in my research. But in some sense, the talk is not really about math. Pretty bold statement for a math talk to make. It's really more about like, this is what it can be like to do research. This is what it's like when you get stuck. Here's what it can look like when you get unstuck, or what that's like, and looking for the people who have sort of helped get you there. So I'll kind of bounce back and forth between talking about math and then also like breaking and sort of telling a little story about like myself or some people that I've met along the way. And I guess maybe I'll also preface, like, I've never really given a talk like this before. You know, most math talks are just like theorem, example, maybe some proofs and pictures, and there's maybe some of that in this talk. But I'm trying to give you a little bit of a story too. Okay, so who am I? What does my research look like? I'm an algebraic combinatorialist. What that means is that I mainly focus on discrete things. So I like to say discrete data. Everybody really likes data right now. And I like organizing that data. And what this can look like is looking for some kind of structure. In this talk, I'm going to focus on a lot of like geometric kind of structure. But oftentimes it can be more algebraic. If you kind of have taken some kind of abstract algebra sort of thing, you enjoy looking at symmetry. That's also something that comes up a lot in my research. But many research questions for me start out with something really simple. I like two questions. And the first question is, since I'm looking at discrete things, you know, like how many apples are there? There are 5 apples. I ask the question, how many? Very simple question. And we kind of know what the answer should look like, which is nice too. You expect like a non-negative integer. Can you all hear me okay? I thought I heard a little feedback. Give me a thumbs up if you can hear me. Okay, some people are alive and awake. Oh, great, awesome, good, thanks. Okay. The second question that I ask is, how do the things that I'm looking at compare with each other? Like, this is the organizational part. Is there some framework that I can use to sort things like, oh, well, this is in some sense bigger and these ones are smaller. Now, okay, the how many question, how many apples are there? There are 5 apples. We know the answer should be like a non-negative integer. But what does the answer look like? What's the data type? Or how do they compare? That's maybe a little weirder. So let me tell you what the answer can look like. The answer looks like a partially ordered set. This sounds very fancy, but it's not very fancy. A Poset for short. So you got some set of things, some discrete set, and you want to compare them. So what does comparing mean? What are some of the rules we expect comparison to play by? Well, you should be able to compare to yourself. Like, you kind of know something, there's a reflexivity. Also, if I'm bigger than you and you are bigger than me, maybe we're just equal. That's the anti-symmetry. And transitivity maybe is the most sensible one. If I'm bigger than you and you're bigger than Reed, then I'm bigger than Reed. Sorry, Reed. So these are the rules that we expect partially ordered sets to play by. Essentially, what we're saying is I should be able to say when X is less than Y. But not every pair of things necessarily needs to be comparable. Maybe there are some things that are just so different, I can't really say that one is bigger than another. So the picture here below, which actually looks a little fuzzy, this is an example of a Poset. Maybe I'll zoom out. Okay, so what's the elements of this set are sets of the numbers 1, 2, 3. So think about choosing. I could choose none of the numbers. That's the thing at the very bottom, the empty set. I could just choose one number, like just 1, or just 2, or just 3. I could choose 2 numbers, 1, 2, or maybe 1, 3, or I could choose everybody. Those are the elements, and I'm going to say one set is smaller than the other if the things in the smaller set are contained in the things in the bigger set. So like if I chose 1, this guy, that guy is contained in the set 1, 3 because the element 1 is in the set 1, 3. So I'm going to say it's smaller. And the way that I represent it visually is smaller stuff is lower down in the page, and as you get bigger, you're moving up. So that's an example of a Poset. That's what it looks like to ask, like, how do things compare? Okay. So I have 2 other kinds of definitions, and then you guys are gonna be ready to do something, okay? I'm just giving you a little warning. I'm gonna ask you a question soon. Okay. So when we talk about Posets, you might want to say, well, like some things are really close together. Like they're like, it's just a little bit bigger than the other one. There's like nothing in between them. That's what's called a cover relation. So if I have 2 things like X is less than Y, and there's nothing between them, we say that X is covered by Y. The other notation that I occasionally use, but maybe not so much in this talk, is that in some Posets, there's a very biggest element, which I usually write as like 1 with a little hat on top. And there's I have a typo. So sorry. There's a smallest element, which I usually write as 0 hat. Okay. So I like to look for structure. One of the kinds of structure that helps me organize things, organize my data. So maybe I got a Poset, but then I want something else, something extra. The extra is what's called a Lattice-Poset. And you could think of it as a kind of multiplication. This is an operation which takes two elements of my Poset and produces a new thing. And here's how it works. In a Lattice-Poset, each pair of elements, U and W, so I'm going to take two things. For each pair of elements, U and W, I can always find a smallest common upper bound. A smallest common upper bound, and we call that the join. I thought I had my highlighter on. And then kind of dually, like going in the opposite direction, there's always a greatest common lower bound for them. And we call that the mean. Okay, so here's where I'm going to ask you to be a little interactive. On the next slides, I'm going to show you a Poset. So it'll look like some elements which are going to be represented as like vertices, and they're ordered where small things are at the bottom and bigger things are at the top, and cover relations are like these edges. I want you to tell me if you think this Poset is a lattice. And if that sounds like, oh, this is going to be really hard, just focus on the first of these two, the join. Check, okay, for any pair of elements, could I find a smallest common upper bound? Something above both of them, and it's like the smallest thing above both of them. And I'll let you know, none of these are huge Posets. This is going to be doable. Okay. Let's look at that first example. What do you think? Do you think this Poset that we're looking at, which is like subsets, for any pair of subsets, can you find a common, something above the two things, like maybe choose randomly, two guys. Is there something that's above both of them, which is like smallest and above both? One person's like, bam, I think this is a lattice. So go ahead, take a minute. I'm gonna wait for people to actually make some reactions. So right, thumbs up is, yeah, I think it is. Anything else, like the crying face, you could say, no, I don't think it is. Even if you make just like a guess, that's okay. Yeah, you could put in the chat if you're like, I'm not brave enough to broadcast my opinion. That's totally fine. I'm going to wait just a little longer. Maybe there's like, this is tricky. I'm not sure. Not sure what to look for. Okay, so if you're one of the people who's like, I'm not really sure what I'm supposed to look for, that's okay. I'm gonna help you out. So let's just grab two things about two guys which are not comparable, because if one is already bigger than the other, then the bigger thing is the common upper bound. So it's like a little somehow like too easy. So we're gonna grab two things which are not comparable. Like, how about just 1 and 2? Is there something that sits above both of them, which is like the smallest thing? Let's see. I mean, the big 1, 2, 3 is above everybody. So that's a common upper bound. It's above both of them. Is there something which is above both of them and even smaller than the 1, 2, 3? If you think so, you could put it in the chat. Yeah, exactly. Jacob, thanks. Yeah, a couple of people are suggesting like, wait, what about 1, 2? That's above both of them. I can see there's like, they're connected by edges and they're going up. And it's still smaller than the 1, 2, 3. Yes. Yeah. 1, 2 is the join of, it's the smallest common upper bound. Okay, so yes, this guy is a lattice. This is a Lattice-Poset. And what in general, if I have two elements in this Poset, what the join is the union, right? Because if I have two sets, what's a set that contains both of them and like nothing extra? It's just the union. Just take all the elements of both sets and nothing else. And that's exactly what 1, 2 is. It's the union of the set 1 and the set 2. Yeah, and actually the symbol, let's see here. The symbol looks like this. It's like a pointy V. It's meant to make you think of the symbol for union, which is like a U. The similar thing for, and even the word join, it's like you're joining together the two sets to make a bigger set. The meet was the one where you're going down, you find the greatest common lower bound. And it's similar, it's really just their intersection. It's where the two sets meet, literally. That's the things they have in common. Okay, so that was like a little warm up. And maybe that one was already kind of tricky, but so you have a strategy now. Pick two things. Maybe they could be kind of close to each other even. And just check. Is there some smallest, a unique smallest thing which is above both of them? It's probably going to be kind of close. I'm not going to show you like any really huge posets. Are you ready for another one? Slowly scroll. Let me know if you have a question. If you're like wanting me to stop and pause. What do you think? Do you think that one is a lattice poset? Right, thumbs up means yes, I do. And this one actually, right, it has a symmetry. Like if you flipped it upside down, it'd be exactly the same. So you really can just focus on this like smallest upper bound thing. And if you think you can find a unique smallest upper bound, you're good. If not, then no. What do you think? Give me, I'm going to wait a little while. Wait for your reactions. Oh. Also, so many people, I looked at the participants list and it was like 17 and all of a sudden there's 43 of you here. So welcome. Victoria, I really enjoyed that. Thank you. Nice. So sad. There's a lot of variety in your reactions. Yeah, it's going back and forth. Who knows? Oh, what is it going to be? It's tricky. Should I give you more time, or I'm seeing a lot of responses. So I feel like maybe you're ready to talk. Okay. So I'm just going to pick two things which are not comparable. I'm going to actually kind of like before, I'm just going to pick something that's kind of close to the bottom here, like these two guys. I guess this is a poset where the elements are like strings or permutations, orderings of the numbers 1, 2, 3. And somehow they're being ordered by like how out of order they are. So 1, 2, 3 is in order. And then like at the very top, 3, 2, 1 is really out of order. Okay, these two guys. So again, there is a biggest element in this poset. So it is a common upper bound, but we could do better. There's also, maybe I should ask you, is there another common upper bound which is smaller than the 3, 2, 1? You can throw it in the chat. Yep, yeah, so 2, 3, 1. And 3, 1, 2. So that's interesting because those two are sort of on the same level. They're not comparable. They're both minimal upper bounds, but there's not a single smallest common upper bound. So there's no unique smallest upper bound. So yeah, this one is not a lattice. So it's kind of tricky. I think in the definition, you might think like, oh, this is about just finding upper bounds, but it's not. Good question. Okay, let me look at that question again in the chat. So you're saying, what would you do if you took the join of 3, 2, 1? Tim, I'm gonna try to repeat your question and you can tell me if this is correct or not. Am I saying your question, relaying your question accurately or not? So if I was taking the join of 3, 2, 1 and 2, 3, 1, would there be no upper bound because there's sort of nobody bigger than 3, 2, 1? So I guess upper bound is somebody greater than or equal to the things in question. So 3, 2, 1 is greater than or equal to both elements. So if you have an order relation, since 3, 2, 1 is already bigger than 2, 3, 1, you're looking for in something bigger than or equal to both of those. And 3, 2, 1 fits the bill. And it is right. That's actually the only thing that's bigger than or equal to both. Not a lattice. So here it's not that we don't have upper bounds at all. Like everybody actually, any pair of elements has somebody who's greater than or equal to the things in question. It's really that we don't have unique smallest ones. Yeah. Ryu Feng, sorry if I'm saying your name wrong, but go ahead.
You can call me Leo. So in this definition of the lattice, does it necessarily mean that every element must be connected to another element in some sense?
Yes. Yeah. So if you thought about the picture that I'm making is called the Hasa diagram, but it's a graph. It's like vertices and edges. Okay. I would say that if your lattice is finite, then that's a connected graph. Yeah. Infinite stuff can get kind of funky though. Okay, cool. Let's do another example. It's fun to learn new definitions. Okay, I just got rid of the X in the middle. What about now? So I got rid of 2 of the order relations from the previous slide. Is this thing a lattice? What do you think? We could just focus on those 2 elements again, kind of close to the bottom. Do they have a smallest common upper bound? I think a lot of the time as we think about this stuff, there's a lot of disagreement. It's really interesting. As soon as I see one person's response, I see the opposite too. Maybe the other example, you're like, oh, I'm skeptical of everything now. I don't know. So this one, remember at the start, I said well, there's somebody bigger than everybody else. Everybody is sort of connected by edges. So that means remember the transitivity. An edge tells you these 2 things are related and there's nothing between them. And you can walk along edges and still have order relations because of the transitivity. So 213 is smaller than 231. That's a cover relation. 231 is smaller than 321. That's a cover relation. And then the transitivity says, oh, well, 2, 1, 3 here is smaller than 3, 2, 1. That top guy is bigger. It's an upper bound for everybody. So there is an upper bound. There's actually only one upper bound. That's it. So just by the fact that there's only one, it is the smallest. There's, you know, in the set of upper bounds, there's only one thing and it is the smallest, which I know sounds funny because it's the biggest thing in this poset, but it's really about comparing different upper bounds to each other. So the difference between this example is the pink thing and the blues, those are my possible upper bounds. When I think about comparing those among each other, both pink things are minimal. There's not a unique smallest thing. In this example, there's only one upper bound. So when I compare it to the set of upper bounds, yeah, there's a smallest thing only just because there's one thing in there. Okay, I'm going to show you some more examples that are kind of, I said earlier, maybe you hadn't joined yet though, even. I said earlier that like in this talk, I'm actually going to talk a lot about things that are like very geometric. So I don't know, they're things, I wouldn't calling them like real world as maybe stretching it, but they're things you could like kind of hold in your hand. And that's sort of true for the remaining examples. Okay, what do you think? This poset. What's going on here is you've got 1, 2, 3, 4. And then anytime you see like in 1, 2, if you see the 2 in another element, it's going to be above. So just this guy. There's going to be an order. It's almost like a subword type thing. If I use the 2 again in another element, that's going to be an order relation. I used the 2 again in this element. So 2 is less than 1, 2, 3, 4. What do you think? If I pick any 2 elements, we could pick some things close to the bottom. Do they have a smallest common upper bound? I know, now you're like, I question everything. I don't know. I'll give you a moment. Maybe I won't let you spin your wheels too long. Jacob has a question. Go ahead, Jacob. You can put it in the chat or say it out loud.
That question is dependent on if this is Lattice-Poset or not, so I will wait to ask that question. I was meaning to do a reaction, but misclicked. But I actually have a question later, perhaps.
Okay. All right. Let me perhaps show you. Oh, I don't know. Yes, no, it could be either. I'm going to show you the next slide. It's going to give it away. This is a lattice. And it's called the face lattice. So imagine you have a square. That's something you could like hold in your hand, right? And you look at the faces. So like vertices, edges, and then the whole big square face. And you just order it by like, oh, is this face contained in another face? So 2 vertices, neither one is contained in the other. So they're not comparable. But a face is contained in an edge, and that edge is part of the big square face. And like, so actually this is like a lot like the subsets example in some sense. Yeah, this guy is actually, this one is a lattice. So I guess I had picked the 1 and the 3. What's a common upper bound? Well, I always know, I guess there's a top element, the square, the face that is everybody. The whole square contains everybody. And there's no edge that contains the 1 and 3. So actually the only common upper bound of 1 and 3 is that 1, 2, 3, 4. So kind of like the previous example, they have a join. For other pairs of vertices like 1 and 2, well, they are contained in an edge together. That would be smaller than the 1, 2, 3, 4, and it's sort of their unique upper bound. Okay, now Jacob is like, okay, ready, I've got my question, go for it.
If you picked 0 and 1, they are have two smallest common upper, what was it called? Both 1, 2 and 1, 4 are equal distance from and
These guys?
oh yes, they 1, 2 and 1, 4 have equal value or is on the same level, but or a shared distance now from who's the smallest common, not denominator, what was the term?
Upper bound.
Upper bound of 12 and 14, because it looks like it could be both of them.
For the 1 and then the empty thingy at the bottom.
For
They
the
pick-
1, because it seems like there are 2 in this case.
So oh yeah, maybe I didn't explain. This is like the empty face. So the empty face is contained in everything. And so if I think about, okay, what face contains both the empty face and the vertex 1? What face contains both of those and is smallest? Well, actually 1. 1 contains itself and it contains the empty face. So the smallest upper bound is actually just the vertex 1.
Okay, that makes sense. Thank you.
I feel like it's a weird, when there's an order relation, I think it's almost harder because you're like, oh, right, one of them is the join. Just gonna look at the chat for a moment. Yeah. Okay, last example that we're gonna follow along a little bit. Okay, this is a small, so only 4 elements. Maybe the labels for the elements are kind of funny. So at the very bottom, it's like R3, like think calculus. You're sitting in a 3-dimensional space. And then if you go up a level, let's see, what does it say? It's like a vector such that like x1 equals x3. What is that? Oh, it's like a plane, actually. So it's like a plane cutting through R3. x2 equals x3. Okay, that's another plane. x1 equals x3. That's the third plane. Okay, so I've got 3 planes. And then up at the very top, x1 equals x2 equals x3. Oh, that would be like a line, actually, in 3-dimensional spaces. That would be like a line. So I've got 4 elements. There's a smallest thing at the bottom. There's these other 3 elements which are not comparable, and they're all below this top thing. What do you guys think? Is there a smallest common upper bound for any 2 things? I just pick 2 of them. Take a moment. Yeah, maybe is this the hardest example of all? The smaller it gets, the harder it gets. Could be. Okay. I'm gonna scroll. I don't know if I'm missing extra reactions. Okay, I think I have one slide between this, so I'm gonna tell you the answer first. So there's a top thing, always, top thing is always going to be an upper bound. And with the two yellow guys that I chose, that's the only upper bound actually. So kind of like some of the other examples we've seen, when there's only one upper bound, it is the smallest. And there's really nothing special about the two things I chose right here. Any of the three, if I choose any pair of the three elements at this, the three planes at this level, any pair of them, there's only one upper bound and it's the top guy. Yes, I'm going to describe what this guy is kind of geometrically in a minute, where we're going to actually see like, oh, well, that's what the join is, like, that's what we're doing. And I have a kind of open-ended question for you. So, and maybe also to back us up, because I just want to remind you, what's this talk looking like? I'm going to tell you some math things, but in some sense, that's not the point of the talk. The point of the talk is more like, this is what research can look like. This is some things that have helped me when I have gotten stuck doing research. This is some of the things that I do when I'm doing research. And one of the people that I'm going to feature, that I'm going to talk about in the course of this talk, Patricia Hirsch, she gave me some advice early on about like a good habit when you're early on thinking about mathematical research. And she said, like, just ask yourself questions. So, I mean, you could do that here. I just gave you a new definition. Is there anything that you notice? Is there anything that you think would be an interesting question to ask? You could write it down for yourself. You could put it in the chat. Like, I'm not really there's no right answer here. I think, so Patricia just encouraged me, like, anytime you hear a talk or you read a new paper or you see a new definition or you're talking with somebody, just write down questions, because I mean, it doesn't matter if they're silly or so hard you would never figure out the answer, or so easy that they seem stupid. Like, it's just good to get in the habit of asking questions. So maybe take a minute and think, what's interesting about posets to you, or any of the examples that we've looked at? This, by the way, is one of my favorite posets, but I just put it here. It's just making a cameo. It's not really featuring in this talk. It's another kind of geometric poset where you have a sort of polyhedron, but instead of looking at the faces to get your poset, you look just at the vertices and edges, and this is telling you who's bigger and who's smaller. Okay, so one of the last example we just looked at, that's a poset. This is called the intersection lattice. So I really took three planes in space and I drew those with GeoGebra. This is like extremely not fancy. And the three planes in space all intersect in a line, and that line is the line where x1 equals x2 equals x3. And that is what you're staring at on the right. So I think the red plane is where x1 equals x2. I think the blue plane is where x2 equals x3, and the green guy sort of slicing through the middle is where x1 equals x3. And the way you could think about building this poset up is you like imagine you're floating in space, in three-dimensional space, and then you grab one of these planes, and that's moving you up. Like now you're in some kind of smaller dimensional space, and now you're going to grab another plane and look at their intersection, and that's a smaller dimensional space. It's actually the line. And in theory, you could keep grabbing planes, and maybe as you're grabbing new planes to intersect with, it actually makes the dimension get smaller and smaller. Here, even when I grab, say, x1 equals x2, okay, now I'm in a two-dimensional space, intersect it with, say, x1 equals x3. Now I'm in a one-dimensional line. When I intersect with that third plane, I actually still stay in the line. So that can happen too. The join is actually just intersection in this poset. If I have two elements of the poset, two elements would be like some collection of planes which I'm looking at their intersection. If I take those two subsets and then intersect them again, that would be their join. So something like, again, very, I want to say you could hold it in your hand. Like this is like a real, it's something in space. It's not totally, to me, this is not totally abstract. You're allowed to disagree though. I also like this example because there's a kind of combinatorial model. Let me zoom in on my pictures. Oh, it's sort of blurry, which is too bad. Let me look at your question again real quick. Yeah, absolutely. So the question, so Jorge asks, is there some kind of like limit on the dimension? So what can happen with these posets is the sort of like the limiting factor is how big your ambient space is. So I chose to let this live in R3, which means that as I intersect planes, like eventually, it's not going to take super long before I'm just like at a single point, like a 0-dimensional subspace. And that's the smallest I can get. So if your ambient space sort of limits how many things you can intersect before you hit something that's 0-dimensional. What these posets end up looking like is sort of like short and fat. And kind of sort of see here. I'm actually going to see when I have this open on my computer, are the graphics better? So I think the program that I'm using to share my PDF has reduced the quality of my pictures. So I'm thinking about switching where I'm sharing my screen from. Hang tight one moment. Oh yes, this is just so much better. Okay. I'm gonna stop sharing my screen from my iPad and switch to my computer. Okay. Sorry about that. All right. So can you all see my slides? Would you mind just giving me a thumbs up to let me know that you're able to see what's going on? The downside to this is like I have to scroll through your part, like all of your pictures to see you all, but that's okay, I don't mind. Great, thank you. Thanks, good. Okay, so we are just talking about, okay. We were just talking about this poset. Okay, there we go. So there's a combinatorial model for these intersections of planes where, I mean, look at the planes that I'm interested in. They look like x1 equals x2. Like the coordinates are being set equal to each other. So instead of actually just writing x1 equals x2, we could sort of like just take the indices, the 1 and the 2, and say, let's put 1 and 2 in a block together. They're equal. And anything else where I have some freedom, I'll just leave alone. And that's what you see over here to the right. So these are called partitions. At the very bottom, there's like no condition about how the coordinates x1, x2, x3 have to relate to each other. They can all do their own thing. But then when I go up to x1 equals x2, now there's a condition on the first and second coordinate. They have to be the same. So I'm going to put them in a block together. And then x2 equals x3, it's similar. I'm putting 2 and 3 in a block together to remind me like, oh, right, those coordinates are the same, but there's no condition about what x1 is doing. It's allowed to be different. And then similarly for x1 equals x3. All right, so you can really think of this intersection lattice as a poset on partitions. A partition is where you have a collection of stuff like 1, 2, 3, and you put them in boxes where everybody gets a box and the boxes don't overlap. So 1 and 2 are in a box together. 1 is not also in a box with 3. It's just in a box with 1 and 2. And how do you move up in this poset? Well, you move up by merging boxes, by putting things more together. So at the very top, everybody's in the box together. And maybe that also makes clear this question about dimension. So at the very bottom, like everybody is as spread apart as possible, But if you only have 3 elements, there's only like so many ways you can merge them together. Okay, so I like this whole hyperplane geometric kind of stuff. And in grad school, I had a professor who was teaching me about combinatorics class, and they also really like this hyperplane stuff. And they're like, oh, Emily, you should look at this paper, which is about lattice-posets and hyperplanes. And I read it and I thought it was really beautiful. And so I was like, okay, research question, maybe you would like to look at it. I was really excited. This is the first research I'd ever done, ever. And I, like I said, didn't know what it looks like to be a mathematician or to do research. So I'm going to tell you a little bit about this problem. And like, as I was making these slides, I remember thinking like, wow, this was like a really ambitious first project for somebody. And I just want to preface, this next definition it's something I'm going to come back to, but it's okay for you to like turn off your brain a little bit and be like, it's 9:30 here. I'm real tired. I'm not, this is hard right now. So I'm just going to let this be a little bit in the background. If you're in that place right now, it's okay. You don't have to feel guilty. Sort of the point of this next part of the talk is this was really technical and tricky. Okay, so let's talk about planes. A plane is really like, it's a subspace, a bunch of vectors where you can add 2 vectors or multiply a vector by a number, and you stay in that set. So it sort of looks, in 3 dimensions, a plane looks like a flat sheet of paper. And a hyperplane in general is a subspace where you're using all your dimensions except 1. So if you're in 3 dimensions, you're using two of the 3 dimensions. I like hyperplanes. Right. In the picture where we're looking at this intersection lattice, one thing that you might sort of notice, like I didn't go all the way down to a 0-dimensional space. So in some sense, there's like this extra dimension that I wasn't really using. And we can simplify this picture by like slicing through our 3 planes with a 4th plane. And then like, imagine like taking that blue, green, and red star and just like smashing it into the paper, into that blue like sheet of paper. And what you would get would be the picture on the left here. Really, that's like the real information that you need. Like you have these 3 things and they all intersect in one common face. Right? So in this project that I was given, in my first research project, it was looking at an arrangement of planes like this one, and then you kind of break apart some of the planes. And the rule for breaking them apart into some pieces, like imagine shattering glass. So you're going to break things into pieces, which are called shards. The rule for doing this is if you, and I'm actually lying to you a little bit because the rule is actually a lot more complicated than I want to tell you. So I'm telling you a simplified version. The simplified version of this rule is if you see 3 planes together, and when you see 3 planes together, like in this picture, you choose a special little region, which I colored in yellow. You choose a special little region, and then the plane which doesn't touch that region gets broken apart. It gets smashed in the middle. And the 2 pieces are called shards. And so where before the planes were defined by equations that looked like x1 equals x2 or x1 equals x3, now a shard is also defined by like x1 equals x3. That's this guy right here. I don't know if you guys can see my mouse. I hope you can. And then an additional inequality that relates like x1 to x2. It says, oh, well, x1 is bigger than x2 in this piece, and x1 is smaller than x2 in this piece. So my project was to look at these planes in various different types of what are called reflection groups. Okay, cool. And in various dimensions. So when it's 2-dimensional, you can be like, yeah, okay, this is fine. I could draw this. But the thing is, we don't just want to stop at 2 dimensions. We want to think about 3 and 4 and 5 and like n-dimensional things. And I just want to show you like, this is what it can look like if you go up just one extra dimension. This crazy picture is where I've taken actually planes that live in R4, which I really can't draw for you. And then I intersected them with a sphere. And I just am looking at actually the top of that sphere, the northern hemisphere. This is what the northern hemisphere would look like for this particular arrangement. The black circle around this black circle is the equator. And I guess you can kind of see through the sphere a little bit. I sort of wanted to show you it looking a little spherical. And then the picture in the middle is if you imagine putting a hole in the South Pole and then like stretching out the sphere so that it would lie flat on your sheet of paper. And now where these planes intersected the spheres in these big circles, they get stretched out, and some of them get stretched out into big circles. And then some of them are actually kind of stretched into sort of smallish circles. It kind of depends on the angle at which they were intersecting the sphere relative to like the North and South Pole. But you can still play the same game. You like pick a kind of special region and look at which hyperplanes don't touch it and smash those hyperplanes. And at the end of the day, the things that define these funky things called shards, you get an equality like x1 equals x4. And then for the numbers between 1 and 4, 2 and 3, you have to say you have some inequalities like x1 is less than x4, sorry, x1 is less than x2, or x1 is greater than x3. My research project was to look at shards and define a poset on some subset of these, which would relate to a different poset. And I'm going to show you what my process looked like as I was trying to get my head around this stuff. I was reading some really hard definitions and just trying to remember them. I was trying to construct specific examples, and in some situations I could, because I could like draw them or I could write down the inequalities. But in some cases, I really couldn't construct examples because there was no kind of combinatorial framework. Like for these intersecting hyperplanes, for these intersections of planes, we could model them with partitions, but for shards, it didn't seem like there was anything in the literature for that. I was really getting stuck and kind of frustrated, like maybe I'm not good at this. And like, I didn't know that you're kind of allowed to get stuck when you're doing math research. It's like a pretty normal thing. So I sort of internalized this as like, well, I must not be very good at this. This is the sad part of the talk. Gosh, that's so hard because I think, so Marco is asking like, what's the most difficult part of your research? I feel like it's also changes with the research questions. A lot of the time early on, I think it's just like getting your head around the definitions though, right? Because like, okay, secretly, I didn't even need to tell you guys what a lattice-poset was. I just wanted to show you a new mathematical definition. That's hard though, right? It's like hard to kind of like get used to something new. And math definitions aren't always super user-friendly. But I think it shifts, like early on, maybe just coming up with examples is hard. Maybe you get better at that, but then it's hard to actually write the proofs down. Sometimes you like actually maybe feel like you understand it, and then the hard thing is communicating about it. It's like, I feel like all of this is challenging. Yes, so Sri Young, I apologize, I must be saying something, like saying your name completely wrong, was asking, is there anything like a coset in this context? There totally is, actually. There's like really a whole thing I could have talked about with like quotients that really mimics like group quotients, if that sounds like something that you were thinking about when you wrote that question. So yeah, I like you guys are really interacting, which I love. So I don't need to pull us away from this slide. So I'm gonna grab a drink of water. Yeah, okay. So I was just asked, like, what did you do when you got like you're stuck? What did you're so in early grad school, like for first research question, felt stuck, felt like, am I even supposed to be here? Well, I'm still here, so something must have happened. That's what my next slide's about. So I was really lucky in grad school because I don't know, I think that something about the timing was just right, where I met a lot of different types of people doing different kinds of math, maybe like a fair amount of combinatorics, so things that I like, but really not the same things. And I kind of want to talk about what they did to help me. And I think, and I guess, so the people I'm going to talk about are Erin Bancroft, Ruth Davidson, Patricia Hirsch. I'll tell you more about Erin in a little bit. Both Erin and Ruth were grad students, but more senior grad students than I was when I was in grad school. Patricia Hirsch is a mathematician and she was a faculty member at my grad school. You know, I think maybe Ruth of this group was somebody who was actively encouraging me and would say things like would maybe, if you think about, oh, you're feeling stuck, you need somebody to like encourage you. She was somebody that really encouraged me, but really that's kind of not what got me unstuck, which is a little, I mean, having people that encourage you is really important. I think as I was writing this talk, it was sort of surprising to reflect on how much actually just like listening to other people talk about their math and like really appreciating what they have done helped me, even if I wasn't exactly doing what they were doing. And so that's what I want to talk about. So I was stuck, but I was going to like the grad student seminar and to math talks. And that's where I heard Ruth, who is really involved in that, just talk about her stuff. And Patricia Hirsch would just talk about the kind of math that she did. And they were different. It was different from what I was doing, but has some similar flavor. So I'm going to tell you about their math next. Not strictly belonging to them, just something that they have done in the past. So Trisha and Ruth, among other things, study Poset topology or like combinatorial topology. So when you're looking at this sort of thing, what you look at is a simplicial complex, fancy word for a very not fancy thing. It's a family of sets which are closed undertaking subsets. And I might end up pulling up my iPad again so I can draw. I think I want to do that right now even so that I can give you an example. Also, okay, I'm sorry, I didn't see this question earlier. There's a question about if like I'm in high school, like, is it reasonable to do research? And I would say, I mean, it definitely depends on the person, but I think it depends on what you're interested in, but I think yes, I think the answer is yes. And if you're listening to this talk and you're not totally discouraged from doing research at this point, then it's going to get better. But then you should reach out to somebody that you like who does, like, I don't know if you have a high school teacher. I mean, maybe that's a place to start. Anybody who's in some context doing math and just say like, I'm interested. Is there somebody who can connect with me? Honestly, just asking like is just a really good start. Okay, so hang tight. "90 minutes also is a super long time. So it's nice that you just get to breathe for a minute as I do my technology. Okay, I know there's nothing worse than watching somebody scroll. So I apologize. Okay, so what's this? A simplicial complex. So as an example, as a very simple example, oh, that's not big enough for you. Here, we'll do this off to the side. Well, let's say I have a triangle, but it's empty in the middle. So this is an example of a simplicial complex. It's a family of sets. So I've got my vertices. And then really this only has edges. 1, 2, 2, 3, 1, 3. That would be my family of subsets. Every subset here, every element of this family is called a face. The ones which are maximal, like you couldn't make them bigger by adding another vertex, another element, those are called facets. So these guys are facets. The dimension of the face is 1 less than the number of vertices. So like an edge, which is like a one-dimensional thing, an edge has 2 vertices in it. But in your head, if you see the word dimension, you can just think like, oh, it's basically the number of elements in this subset. So abstract simplicial complex, it's a bunch of stuff, but it makes sense to talk about faces is roughly the thing. And it's something you could draw. Again, that's sort of like a theme. I really like visual sort of geometric things. Ruth and Tricia were looking at simplicial complexes, and they want to keep track of the sort of the shape of that complex. This is something called topology. So maybe they want to know, is it sort of flat and filled in? Is it flat and solid like a disc? Or is it more like my example here is empty in the middle? So it's sort of like a circle. There's like a hole in the middle somehow. So that's more like a circle. Or you could imagine in my picture that I've drawn on the slide, that looks sort of spherical, right? This sort of idea of keeping track of, do I have a circle? Do I have something like a sphere? Or is it more flat and solid? That is roughly the sort of thing that Tricia and Ruth are keeping track of in the mathematics that they're doing. And in particular, they're looking at a shelling. A shelling for a simplicial complex is like a recipe where you take apart your complex based on its facets and take it apart. I really rather think of putting it together. It's a recipe that tells me how to put together my complex using my facets so that I can keep track of whether I have closed off a sphere in making my complex, or maybe I'm just actually making something that's sort of flat and solid. So let me give you we're going to see a new definition. Well, I'm going to define what a shelling is. And we're going to do an example. Math research is sort of about definitions, and it's kind of an awful definition. I'm sorry, but it's really not too bad. We're going to do this example, and you're going to be like, okay, I think this is okay. Okay, so I've got a simplicial complex, like a triangle. When all the facets have the same size or the same dimension, our triangle is like that. All the facets have 2 vertices each. That's called being pure. So if you have a simplicial complex, a shelling is where you take all the facets and you give them an ordering, 1, 2, 3, blah, 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 to M. And the idea is you've created a step-by-step process for making your complex so that every time you can see whether you've closed off a sphere or you have something sort of flat. The way this works is at step 1, you've got just one facet, no rules, just a facet. At step 2, you have some facet which you've called F2, and you're going to take it, and the rule is you have to glue it to F1 so that you're using a maximum dimension boundary of F2. Okay, so if you're gluing 2 triangles together, they need to glue along edges. They can't glue at a vertex. That's too small dimension. They need to glue along an edge in a shelling. At step 3, you're going to take another facet, F3, and glue it on, but it needs to be glued along a maximum dimension boundary. You can tell when you've closed off like a sphere, if you glue along the entire boundary. You're going to cap off a sphere. And that's sort of the beauty of what a shelling is. So this huge union intersection thing is basically what I've described. The rule is when you intersect FK with all the previous stuff, you need to intersect in like the maximum size dimension, the maximum possible size dimension. And what's cool is you can keep track of how many spheres you've glued off, you've capped off in this process, and anything that has a shelling ends up looking like what's called a wedge of spheres. If my spheres are sort of like two-dimensional spheres, they look like balloons that are tied together. This is a wedge of 2 spheres. You don't have to just use 2 spheres though. You could use a 1 sphere too. That's just a circle. And the wedge part just means they're all joined together at a vertex. Kind of neat. So, right, this is totally different from hyperplanes, or it seems really different from hyperplanes and the shard stuff that I was kind of stuck on. I really loved listening to Ruth and Trisha talking about it. Let me show you an example so you can kind of like get a little sense of how this works. This is where on my iPad, the picture quality is so much worse. So I'm going to go ahead and switch back to my computer. Okay. And it says it's loading, and now you can see it. Oh. Okay. Is there a slide you would like me to go to? Let me know if you want me to go back. I think the slides will also get posted. Okay, so here's my simplicial complex. It's an empty tetrahedron. So the facets are like these triangular faces. The middle part of this tetrahedron is empty. And I colored in the facets. It's like not planar, so it looks a little funny. Sort of the right hand 432 facet is blue. The kind of like the facet facing you, the 142 is pink. 134 along the left side is green, and then the very back is yellow. 1, 2, 3, the very back facet is yellow. So I numbered them F1, F2, F3, F4, and that's supposed to be like the recipe for building up this complex. And it's going to tell me like, okay, at some stage, maybe I'll close off a sphere, or I just end up with something kind of flat. That's called, the technical word for this is contractible. So, okay, step 1, I just plop down my facet F1. Great. No rules, nothing to check. At step 2, I'm going to take F2, and along any vertices where they agree, I need to glue. And hopefully I should be gluing along edges. If I don't glue along edges, it's not really a shelling. I've broken the rules. Let's see, F2 and F1 agree on 2 and 3. They both have 2 and 3. Oh yeah, so I'm gluing along that 2, 3 edge. Good. That's a maximum size boundary. Like that's the biggest size boundary. I don't glue along a vertex. That would be bad. Okay, great. So now I've glued F2 in. F3, the rule is glue along any vertices they have in common. Okay, so actually 1, 3, and 4 all appear, but really I only have the edge 3, 4, and 1, 3. I don't actually have the edge 1, 4 yet. So that edge isn't being glued to anybody yet, but I am gluing along edges. I'm gluing along like maximum boundary, maximum size boundary of my F3. So that's good. And if I kind of imagine flattening out that step 3, what I get, like, this looks like a disc, nice and flat. We could imagine just shrinking it until it's just a point. That's what being contractible means. So we don't have any spheres yet. All right, in our last facet F4, 1, 4, 2, all vertices have appeared so far. So I kind of expect I might be gluing along the entire boundary. And yeah, I mean, all edges here appear too. I see the 1, 2 edge, I see the 4, 2 edge, and I see the 1, 4 edge. So this last facet is it's gonna be glued along its entire boundary. And when I do that, you can see I sort of cap off a sphere. I like made that step 3 picture look a little like a bowl. I'm just putting the top on the bowl. And it's empty inside. So it's a little different. I can't shrink it down without losing that emptiness. So this is in some sense really different. The shape is really different than just the disc. Okay. So this is an example of the theorem that I think is being asked about on the previous page. Okay, did you want to ask about, was it this theorem here? I'll give you a minute to look at this. And if you have any questions at all, this is a great place to jump in. We're also going to sort of pause and talk a little bit about like more story time. You got a new definition, a new math definition. I'm going to pause and do a little story time. No problem. Yeah. Yeah, everybody like, take 5, stretch a little bit. 90 minutes is a long time. Although, Pierre Guy, we're going to end around 3:35-ish.
Yeah, that's fine. No problem. We started a few minutes late anyway.
Okay. When I was making this talk, I don't often give 90-minute talks. I was like, this is, oh man, I hope I have enough slides. And now that I'm actually giving it, I'm like, oh man, I might not get through all my slides. Okay. All right, so go ahead and scroll. Here's our Schelling example. I think, so like Ruth was really encouraging to me, but I think what I really appreciated listening to her was just hearing her talk about research, that like she also went through this period of like looking at a definition and just like that kind of technical, like I'm just trying to understand this thing and make examples. And she sort of related it to an experience like with playing an instrument. Maybe some of you are musical. You know, like early on when you're learning a new instrument, you're doing some stuff that feels like it just feels almost pointless, like learning scales. Is sort of annoying. It's technical. It feels tedious. And it's hard to see that you're going to make music someday. You know, like you don't really, it's hard to tell like that there's any art that's going to come out of this. Like, what am I even paying attention to here? I don't know. I'm just doing this thing that hopefully pays off. But actually, Ruth, what did pay off for Ruth, and what I think also paid off for me, even though it wasn't clear to me at the time, was that like those definitions do sink in. Like, even if you get stuck and you're like, I don't see how to make progress with this problem, what you realize later is like somebody asks a different, maybe slightly related problem, and you actually have some traction because you have some fluency. Like the words aren't new anymore. So there was like some hope that like it wasn't for nothing. Like I'm learning something even if I can't tell. Okay, so now we're going to go back to Posets. Right, we had Posets, and then we talked about simplicial complexes. And when you take those things together, you get, boom, a new thing called an order complex. So to any Poset, whether it's a lattice or not, you can make a simplicial complex called the order complex. The elements, the vertices are just the elements of your Poset. And then what are those faces? Those are subsets of the Poset which are totally ordered. That means that any two elements you know who's bigger and who's smaller. There's no incomparability in a totally ordered set. Sometimes we call them a chain because they literally look like you're just always walking up like a chain. Yeah. So we're going to do some examples because we just met a new definition. We saw this subsets example when we were first learning about lattice-posets, right? Got the empty set, then you could do element 1 or element 2, put them together in a set, you got 1, 2, and then you have everybody 1, 2, 3. So I'm drawing part of the order complex here. I've highlighted 1, 2, 3, 4 elements of the poset. They're totally ordered because like you know exactly who's bigger and who's smaller between all 4 of those highlighted elements. And those, what I do is I take them together and I make a face. So on the right-hand side, I've put together empty set, element 2, 1, 2, and 1, 2, 3. And that because at every step in this totally ordered set, I'm actually just going up by an edge. It's somehow maximal. Like I couldn't add anything else into this set without introducing some kind of incomparability. So I have a question. This is supposed to be interactive and you guys have been awesome asking your own questions. But I have a question. How many facets do you think there are in this order complex? Could you guess? How many is a great question because you know it's okay. The type of answer at least is a non-negative integer, and it's actually a positive integer because you know there's at least one facet. I drew one facet. What do you think? How many facets? Do you want to just make a guess, even if it feels like it's completely random? I'm not sure. Yeah, you can put it in the chat. You can make it private. You don't have to. Jacob was brave. He's like, just putting it out there. I'm going to wait for at least three guesses. I've got 2, so you just got to give me one more. What do you think? How many facets? How many different ways are there to walk from the very bottom to the very top? So I won't credit you. Well, I guess you all put it to everybody, so that's great. I've got 4, 6, 7, 6, 8. I kind of see where you're like somewhere in the middle, maybe 5. I feel like you're not, like you're all kind of in the right. Nobody's like 100. That's, yeah. I think this is, by the way, the answer here is so beautiful. It's really interesting. I'm going to tell you guys the answer. There are 6 ways. There are 6 facets. And I drew this like kind of inside of a cube. I mean, the poset already looks like a cube. But you can draw the order complex in like a cube too. And the facets are like it's called a triangulation. You split up this cube into tetrahedra. And all the tetrahedra are going to touch along this long diagonal connecting the empty set at the bottom and the 1, 2, 3 at the top. So imagine putting in tetrahedra that all share an edge. They sort of like radiate outwards. And there are going to be 6 of them. And I think I'll actually explain where the 6 comes from. Like it won't, I'm hoping by making big promises in 7 minutes, by 7 minutes, I'll have sort of explained where that comes from. Okay, one other post that we're sort of following along is this partitions, right? These intersection lattice. And this is what the order complex looks like. This is actually one that Ruth showed when she would give her talk. This is one she would do. And she even had like a manipulative where she had like almost like little flags. They have like 3 triangles and they're all glued together along an edge. And that edge is the edge, which you could think of as like, well, I have a totally ordered set, which is just 2 things. The very bottom, the very bottom is always smaller than the very top. That's a totally ordered set. And really like kind of everybody, all of the facets are going to be glued along that edge always. If you have a biggest and a smallest element, that's always going to be the case. Okay. One person I haven't mentioned yet is Erin Bancroft. So Erin is also a student who was advised by my research mentor. We barely overlapped. I never really got to know her. I think she gave me a ride home once from a math talk. She graduated pretty fast with her PhD, like in 4 years, which in PhD and master's together, which I mean, like 4 years in the French system, if you've already got a master's, it's not that extraordinary, but like imagine you finished your master's and then in a year you got your PhD. That's pretty fast. And she got a position in a small town in the US. And I think she may have left academia. Like I said, I didn't really get to know her super well. But somehow I feel really indebted to her because at some point I read her thesis. I don't even know. I don't think my advisor told me to do it. I just think I was interested and I looked at it. And I feel like somehow it wasn't even that her thesis gave me an idea that, whoa, it became the big thing in my thesis. That's not really true. It was more like I read her thesis and I was like, oh, this is what math research can look like. Like it gave me this example that just felt doable and really, but also really beautiful. It's sort of a strange, I don't know, it's almost hard. Like I've never given a talk like this. So it's sort of hard to describe. Like I feel like she solved a problem that was very specific. Like it wasn't this earth-shattering thing that was going to change mathematics forever. But at the same time, she solved it in a way that was, I felt like very clever and insightful. And I was like, that's what I want to do. I want that kind of research. And I think it really motivated me to like almost think like to be more focused in the kinds of questions that I was asking. Okay, so let me, if I can, talk a little bit about what she did. So Erin was also doing like this kind of shelling thing, but with posets. So when you've got a poset and you've got these facets, like I said, this order complex, the facets are given by like walking along the edges from the very bottom to the very top. And one of the ways you can keep track of a shelling, which is an ordering of your facets, is by keeping track of all of the ways to do that. And a natural thing to do is to like basically keep track of the edges. So an edge labeling is a way to keep track of edges. An edge labeling is a function that sort of gives a label to each of the edges of your poset. And a lot of the time the label used is just like a number, 1 through n. I'm going to give you a specific example in a minute. And then once you've got this edge labeling, like, okay, so my facets are ways of walking from the very bottom to the very top. So in a shelling, I need a way to order my facets. How do I order my facets? The way to order your facets actually is like dictionary ordering. That's essentially what's going on. So a special kind of edge labeling is called an EL labeling or edge lexicographical. It's a fancy word for dictionary ordering. So if you think about a dictionary, right, you've got like all the A's, all the B's, and then how do you break ties between things that all start with an A? You just look at the next letter, right? That's what this edge lexicographical ordering is. It says in any interval, there's always one chain from the very bottom to the very top where the labels are increasing, they're getting bigger as you go, and also it's like the first in this alphabetical ordering. And that sort of tells you how to order your facets. So we're going to make an edge lexicographical, an edge labeling for some of the posets we looked at. Let's look at, this is called Boolean lattice, these subsets. If you want, I was like, oh, they're just gonna have, we're gonna have so much time. I'm gonna make some more interactive stuff. We have like 0 time. So I think it would be a really good exercise to just like come up with ways to label these edges. I was sort of hoping if I asked you this, somebody might actually come up with a labeling that is sort of intuitive, as there's no right answer here. I wanted you to just label the edges maybe with 1, 2s, and 3s in this Poset. So actually, maybe while you're staring at this, I'm gonna try to open up my iPad so we can label it together. Yeah, so Pierre Guy has the slides for the presentation. So you all will have access to the slides. So if you're like, I really wish I had this, so I can label this on my iPad or something. But really it's like a square. I mean, I think if you're drawing the Poset, it's not a super long Poset to draw. Draw like a little cube. And then at the bottom, you're gonna put empty at the top, 1, 2, 3. The first layer is 1, 2, and 3, and then the next layer is like 1, 2, 1, 3, 2, 3. Okay, so let's say I'm starting from the bottom and I go up the edge 1. I want to label with 1, 2, and 3. Well, I just put a 1 in that set. I'm going to label with a 1. Okay, and now from 1 way I could go up is to the set 1, 2. What did I just add to my set? I just added a 2. So why not put 2 there? But I could have gone up to 1, 3. So I think for this label, for that edge, we'll label it with a 3. Then from 1, 2, okay. What did I add in this edge going from 1, 2 to 1, 2, 3? I added a 3. Okay, so I'm going to keep going and label all of the edges. There we go. There's a very natural edge labeling. And what's kind of cool, I think, is that in many of the Posets that I've shown you that have sort of like a combinatorial model, there's like actually like a pretty natural way to label the edges, just given to you by the object. And believe it or not, this is an EL labeling. If I look at the interval from the very bottom to the very top, there's one chain that is increasing, like goes from 1, 2, 3. There's the increasing chain. And it's the first one in dictionary order, because if you look at the first step for the other 2 chains from the bottom, they both start with a later letter, 2 and 3. So they're already later. If I've used the 1, and I'm thinking about other chains that use this 1 in the first step, it's still smaller than dictionary order because the next thing I used was the 2 and not like the 3 is, if I'm breaking the tie between 2 things that start with a 1, the 2 is breaking that tie. It's earlier in dictionary order. So this guy is an EL labeling. Good exercise would be to like go through that definition and check other intervals, not just the big interval. You're right. Thank you. There are 2. This guy should be labeled with a 1, and that one should be labeled with a 1. Here's where I can convince you that there are 6 facets, because every facet, every maximal chain corresponds with a permutation or an ordering, like an ordered list of the numbers 1, 2, and 3. And how many permutations are there? Well, for the first entry, I have 3 possible things I could put in. And for the second entry, I have 2 because I've already used 1. And for the third possible thing, well, I only have 1 choice. Yeah. Every maximal chain corresponds to a permutation, and there are 6 permutations. So the theorem is that if you have an EL labeling, guess what? That's a shelling. I kind of told you that already. And actually, it's really easy to count like those homology spheres, those facets that cap off a sphere. Go through. There's some more technical stuff I could share with you, but I think in the interest of time, I'm going to skip over this. did want to go back to my computer also, which has just much better graphics. I did want to go back to this example though. So remember I said like, okay, some of our Posets have a sort of combinatorial model, like this intersection lattice, we could model with partitions. And then when you go up by an edge, by a cover, you're just sort of merging blocks. So a natural edge labeling is to say, okay, if I'm merging two blocks when I go up, look at the minimum thing in each of the two blocks being merged. Whatever is the biggest min, it's the max of the two mins, that's what you're going to label with. It's a little silly here because the blocks that you merge are size 1 each. So the minimum is actually just equal to whatever that block is. But I've labeled the edges of this intersection lattice in that way. And that's another example of an EL labeling. Oh, can you all hear me? Could you all give me just a thumbs up that you can hear me okay?
Yes, yes, yes.
That's good. Okay, good. Whew. I'm so glad that I haven't, but I am sorry that for at least some of you, the sound was kind of funky. Okay, good, thanks. Yeah, so I guess the point is, I'm gonna now shift to what Erin did. So what Erin did that was really beautiful is she took the shards that I was studying and she gave a model for them in terms of partitions, essentially. And then she looked at a Poset, which is like our intersection lattice, except instead of intersecting hyperplanes, she was looking at intersections of shards. And then she could model that intersection lattice again with partitions. And since we're short on time, I'm just going to show you, okay, this is what this looks like in a small example. So on the left, this was my first little mini definition of shards. You have these 3 hyperplanes. Whenever you have the 3, you pick a special region and you break the guy that doesn't touch that region. And when you do this, you create shards. And in this example, we'll have 4 shards. You'll have 1 big red, 1 big blue, and then 2 green shards. And when I was learning about shards, I could write down the inequalities, the definitions eventually made sense to me. But as I was doing that first research problem and getting stuck, Erin at the same time was writing her thesis. And I guess we missed each other. I don't know, I just missed her. And so when I learned about what she was doing, it was in her thesis. And that's when I saw oh, there's this beautiful model for shards. And it's really you have the way that this works is like intersections of hyperplanes. You create blocks. So things in a block together are the x1 equals x3. So there's this 1, 3 are in a block. And then instead of having 2 just off by itself doing whatever, you say, well, actually, I have an inequality that involves 2, x1 is less than x2. And so to encode that inequality, I'm going to make a Poset, really. I'm going to put the 2 on top or the 2 on bottom to show me that there was an inequality. And when I read this, I was like, this makes so much sense to me. And this was also that payoff of I didn't realize that I had learned the definitions even. I'd gotten stuck in the research and it didn't really occur to me that there was something I still got out of that. But when I read Erin's thesis, I realized oh, this is beautiful and I understand it, partly because I did the hard work of getting stuck and trying to make all those examples or counterexamples and trying to understand these definitions. So Erin made a Poset out of shards and shard intersections, much like the intersection lattice. It looks like they're like partitions. And she was able to adapt the existing EL labelings from partitions to this context. She had a little extra structure. So each of these shardy partitions actually corresponds to a permutation. think I can show you an example. Yeah, here we go. This is a theorem of Nathan Reading. If you've got this on the left is Aaron's model for a shard. So the 1, 4 in a block. And then I have to decide something about the 2 and the 3. They could both be above the 1, 4, both be below, or one is above and one is below. And now from this model, you can read off a permutation. And the rule is you read it from bottom up. And then inside of a block, you put them in descending order. So 3, 4, 1, because 1 and 4 are in a block together, you put them in descending order. And then finally I get the 2. So Aaron defines what's called the placement of a block, which is something that partitions don't have. They just have blocks. They don't have placement. Aaron defined placement to be like, oh, when you do this map from this shardy thing to a permutation, you see where that block fell. So like that 1, 4 becomes this middle thing in the permutation. So it gets placement 2. The 3 is at the very beginning, so it would have placement 1. So she used that placement as a way to make an edge labeling. But much like our partition lattice, the way you go up in Aaron's shard intersection lattice is by merging blocks. So her theorem is in this shard intersection, instead of intersection of planes in shard intersections, you can label by putting the maximum placement of 2 blocks which are merged. And just like when you do this partitions, you merge blocks to go up, you merge blocks to go up in this shard intersection thing. So here's Aaron's EL labeling. Okay, I know I'm like way over, but I have one thing, because there's like a coda to this. So like I can take Aaron's stuff and then write my thesis based on it. Like to me, it was sort of like inspirational. Saw this, I understood it, it made so much sense, and it helps, I don't know, motivate me maybe to just stick with it and think about different types of questions. But it really did stick with me, because then eventually when I started doing research with like my own master's student, it's like, I think we can do this. I think we can do Aaron's labeling on some different stuff. So with a master's student here at DePaul, who started doing research with me as an undergrad, we adapted and I think in some ways kind of improved Aaron's model using a new combinatorial object called non-crossing arc diagrams to give another EL labeling for a kind of related poset called shard intersection of bipartite bicambrian lattice. You don't really need to know the details. The point is like Aaron's work then kind of did really inspire a new research question that sort of, I don't know, really like spread out to other people. In my very first research question, though, the one I got stuck on, part of it was, though, that I was trying to do shard intersections for different types, for other types of planes, which I know I'm not describing in a lot of detail here. And I guess the coda to this is also, I kind of ended up doing it with a PhD student named Ashley Tharp, who's just about to defend her PhD. We, with Nathan Reading, have also taken Aaron's model and used it to describe the same types of objects in, these are called types D and B. And then we added more to it. We did more. We did something called forcing. And this is also kind of inspired by some work with my now colleague, Kyle Peterson. So, I mean, I guess I was going to take this time to maybe write some stuff down. Maybe I should just skip to thank you. Thank you for sticking with me for so long, because it's late and then I've kind of gone over a little bit, but I don't know. I hope you got something out of listening to a story about somebody learning how to do research. Maybe you're also interested in doing math research. Maybe you're in one of your very first research projects. I guess to me, if there's a takeaway, it's this can be hard and you're going to maybe feel stuck and like, maybe even like, I don't know if this is for me or if I belong in this. But I don't know, like maybe stick with it and see, listen to other people, keep asking questions and try to find like what seems like a small question. I think that when you can understand something well and maybe ask what seems like a small question and sort of open things up for you. Okay, thank you all so much.
Thank you, Emily, for this fantastic talk. I wonder, I mean, you've been talking for a while now, but I wonder if you still have a few minutes for if people have questions.
Yeah,
that they would like to
absolutely.
ask
Yes,
you.
yes. Don't need to run. Give me your questions. I'd love to hear.
So maybe you don't have any more questions because you've asked them during the talk, but if you have some, just type them or just raise your hands and open your mic and just ask them. Feel free.
Oh, there's
Maybe
like
they've already.
2:14 in the morning. Oh my gosh. Well, thank you so much.
Some messages go directly to you, I see. Well, there seems to be no questions, but a lot of thank you. That's great.
Yeah, I mean, I like didn't even really define this, but like somebody had asked earlier about cosets, and I said something like, oh, well, you really can do some kind of like quotient thing. And with Lattice-Posets, you can make lattice quotients. And this is really, it does not have to do with, well, yeah, I would say it does not have to do with physics, unfortunately. There's sort of this rule about when you're quotienting things, you sort of like put stuff together. You take something large and like, I don't sort of explaining this so poorly. In a Poset context, the way you could think about a quotient is you have that, maybe I can go to an actual slide just so I have something I can kind of wave my hands at. Okay, so ooh, I don't know if you guys could hear that. There's a thunderstorm here.
No, we couldn't hear it. It's only for
Oh,
you.
there's like big thunder all of a sudden. Don't worry, I'm inside. All right.
If you suddenly disappear, we'll know you have a power outage.
Yeah, right. So in the context of posets and Lattice-Posets, when you have a quotient, what you're doing is you're sort of contracting edges in this Hasse diagram, in this graph, in this picture that shows you when things are bigger or smaller. And you can't really do that just independently, willy-nilly. Forcing is sort of like the rule we use for how you're allowed to contract things. And the whole point of shards is actually to encode that rule. Oh, nice. Yes, that makes sense that you had seen this in classification of surfaces. So actually, yeah, when the first time I saw simplicial complexes was like the first time I learned about topology. And to be honest, like I felt like learning about shelling just made all of that make so much more sense to me. That like, oh, now I understand why the homology is given by these facets, but with a relation, because maybe there's multiple ways of breaking up the space into facets. I don't know. Yeah. Oh, good question. Maybe I can send Pierre Guy something, Weidong, about research materials, because I do know that in the US, there's like a free kind of online research experience that's just open to people. They put out problems and you're just welcome to like work with other people. So I'm going to dig around for that. But Pierre Guy, if you know of this or something similar to this around you, I'm fairly.
I know some undergrad research projects in Canada. I'm originally Canadian, but I
Oh,
don't know
okay.
about the ones in the US. So if you have some links that you would like me to put on the website for the students, I can do that.
Yeah, sure. Yeah. Is there a book you would recommend for this information? It's a really good question. Oh man. What I would recommend, honestly, Lizette, if you're interested, I would like, if you haven't already, I would take a class in combinatorics, like a college level class, if you can. I'm not sure what stage you're at. And if you've already done that, then I might have some books I could also pass along to Pirgi. How would you describe your experiences being female in STEM research? Oh man, that's such a complicated question. I guess like there was kind of a reason I featured a lot of women in this talk, because to be honest, like that was a big, it was, I think maybe one of the reasons that those are the names that came up to me when I was reflecting on this experience sort of tells you something, that like they were having other women around definitely was something that made me feel safer in the space. Yeah, it's complicated. I think this is where actually, yeah, in my grad school, I was really fortunate to be in a department with a lot of women faculty and a lot of female grad students in math. And we wouldn't all be doing the same things, but at least sort of having those people around made a huge difference for me. And I think in times where that hasn't been the case, it's definitely harder. Yeah. So I think, I don't know if you always need to surround yourself by people who are constantly like your cheerleaders, but surrounding yourself by people who make you feel, who are like safe people to be around to say like, I feel stuck. Like, I think that is really important. Whatever your gender is, whatever your thing is. Yeah. Also, I hope that Pirgi can give you my contact information. I could put it in the chat. So if anybody wants to ever just like send me an email about anything, I am happy to hear from you.
What I'll do is I'll send an email on the mailing list of the participants with your email address.
Yeah.
I don't want to put it on the website because I don't know how to do this in a safe way somehow.
Okay. Yeah.
I mean,
it's my work email. So, but okay, that's fair.
Yeah, your work email is on
Yeah.
your website in any case. Yeah, I guess I can do that. I'll do that.
Yeah. Srijan, I think when I was first learning about posets in like the first combinatorics class I took, and I like learned about this like order complex stuff, I was just like, this is amazing. This is so cool that like the topology I had learned about in this totally other place shows up here. It felt, I don't know. I think when you learn about a new thing and you get surprised, that's one of my favorite experiences in math, is when you get surprised by something. You know, like I know that when you see a theorem, when it makes sense and it's predictable, that feels good. You're like, oh yeah, I expect it because I understand. But it's really cool when you get surprised too. And I think seeing like, oh man, the Mobius number is also the Euler characteristic. That's so cool. Oh, how exciting for you. I don't know if I know anybody at Emory. Are you starting undergraduate there or grad school?
Emily, just to say, we don't see all the questions that you see. Some are sent just to you. So
sorry.
No worries.
One person is let me know that they're starting at Emory for the rest of you all, and they're going to be starting as an undergrad. Well, sounds like you're already like ahead of the game, and like you should just start reaching out to math professors and be like, I want to do research. If you're a high school student and you're going to start college, I mean, even if you're not starting college, I would be proactive about asking if you want to do research, because I know at my own university, we have a lot of support for undergraduates, and it just seems like people don't know and don't even know that they can ask. And it's something where in all of my classes, I'm like, you guys, you should do research. We love having you. But then I ask them, has anybody else ever talked to you about this? And they're all like, no, never, which is just, I mean, it's a reflection of us, the professors. We need to do better.
but maybe I can add to this. When a student comes to you as a professor and says, "Yeah, I'm interested in doing research, can you tell me about it?" I mean, it's very rare that a professor will say, "I'm sorry, but I don't have time for you." No. I mean,
Yeah.
of course, I mean, this is something we like to do and we like to share it. So, yeah.
And Victoria asks, could I do research even if I am not in math or science? And yes, absolutely. Like, secret to you, Victoria, at my school, I get really excited when like an English major is like, oh, I kind of liked your calculus class. Maybe I want to keep doing, like, oh yeah, you should do research because I really hope I can make them a math major or a double major. Yeah. And it doesn't have to be in math. I hope, I don't know. I just love learning stuff. I think, I don't know, if you're here though, you probably like math. Regardless of your major, definitely ask. I know at my university, there's no requirement that you have to be a math major to do math research or a computer science or science major. It's just, are you interested? Can you commit to thinking about it? Well, thank you all again so much for your enthusiasm and all of your questions.
Well, thank
Yes.
you very much, Emily.
And Victoria, also, I really you were very responsive. So like very engaged. I appreciated all of your responses throughout the talk.
All right. So if you don't see any more questions on your private chat, I don't see any more on my side. Maybe we
and
should.
It's very late for you. Thank you, Pierre, for staying.
Oh, well, thank you. Thanks everyone for staying. Thank you for staying so long and answering all those questions and engaging with the audience in this way. It was really nice.